Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Vanshree Bhalotia with us today. Hello, Vanshree.
Hi. Thank you so much for inviting me. It's really a pleasure for my work to be recognized by you and to be here on the series.
Well, thank you so much for agreeing to talk about your very lovely article, which we'll get to very shortly. Let's see, I understand you also do a little humanities, a little art.
Yes. So I'm an artist. I'm a science communicator. And a lot of the work I do in terms of communicating the science is interdisciplinary. And so I think that sort of comes to my science as well. Like, for example, the star that we're going to talk about today. I know stars, we can't name them. And the technical name is KIC 110295116.
Oh, that was very good. That was very good.
Don't ask me why I know that. I just know that. But I've named it Papayu, and Papayu, if there's any Gujarati speakers in the audience, they would know that like Papayu means papaya in Gujarati. And so in like Gujarati culture, normally on Sundays, we have a certain dish we eat. It's called jalebi gathia.
Cool.
And jalebi is like a galaxy looking dessert.
Okay.
And Papayu is like, they serve it like a salad with this jalebi and stuff. So I named it in my mother's mother tongue because I just want to honor the matriarchy. And even if you look at the papaya tree and the way it grows, it's very matriarchal in nature. So it's my first big discovery, and I really wanted to honor the matriarchal side. So I've named it in Gujarati, which is my mom's mother tongue. So thank you to any Gujaratis watching, and I hope you feel connected to Papayu and everything. So yeah.
Well, that sounds like a dish I'm going to have at some point. So I'm going to add that one to my must have culinary taste.
Yes.
So,
yes, definitely.
Cool. Very cool. And Vanshree, what do you like to do for research?
Yeah, so I really like talking about stars, astroseismology, gyrochronology,
Okay.
and looking at stars, because what I believe is if you know your star, you know your planet. And so knowing stars, I feel, are really important. And that's what I like to think about. So
Very cool.
yeah.
Very cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. A new Asteroseismic Kepler benchmark constrains the onset of weakened magnetic braking in mature sun-like stars. And Vanshree, take us away.
Yes. So, this work has happened over a couple years, and this work would have definitely, it's even spanned a couple institutions for me. And it's would have definitely not been possible without my co-authors, because my co-authors supported a lot of the modeling efforts, a lot of the statistical analysis, the refining of these results, and even the plots and everything that I've made. They really supported me in communicating these results.
Cool.
So I really appreciate all my co-authors and all their feedback over the years. So thank you to everyone across the globe who's helped in making this a possibility. And especially thank you to like the software developers and the Kepler telescope and all the people who work on the archival data, because that is how we've discovered this star, is from archival data. So thank you to everyone who works on all of those missions and softwares.
Good shout out. Good shout out. Okay, let's go into it.
So I guess I'll just start with like a little overview of what we're looking at. I know this chart is for astronomers, but I also have an understanding that not everyone in astronomy is as familiar with astroseismology and gyrochronology.
Okay.
And so I'll just talk a little bit, like a little introduction about it. So when we think about stars, like we can think about all stars as quaking. So if you had to imagine what a quake looks like, you could think of like if the earth was quaking, but the earth didn't have a crust, it would just be like wobbles on the surface of the earth. And so all these wobbles are called like star quakes when we look at them in stars. And all stars do have quakes, but often you can't find them because these are on the orders of like parts per million. So
Yes.
finding a star quake is like looking at candles on the surface of the sun, like looking at one flame from one candle on the surface of the sun from Earth.
Very good.
That's how small those odds are. So that's why it's difficult to find these quakes, and also because they get suppressed by larger activity precursors like solar flare or like stellar flares and things like that.
Mm-hmm.
But there is a connection between star quakes and age, and I'll get into that in a bit. But I just want you to know that there's things happening on stars that we can use to find their ages, and there
Cool.
are different types of things. So I mentioned that I was an artist. The way I think about it is I think about like a quaking star that is rotating. So in a way, I think about it as kind of this dance. So not only is the star rotating, but it's also quaking. So it's like a lot happening at
You're
once.
all over the place. Very good.
And yeah, and so I just think combining both of these types of motion can help us understand the correlation between them.
Mm-hmm.
Specifically the correlation between stellar age and rotation periods, which is not well understood at all. There's been like giga years of difference depending on which type of model you choose for how stars age as they rotate.
Yes.
So there are things that still need to be ironed out, and the discovery of Papillon is just one star. It's just one star, but it happens to be a benchmark star because it anchors the points where the models that predict how stars rotate as they age, it anchors the point where those models diverge.
Cool.
So it happens to be a special star, and that's why there's a paper on it. That's why they published it.
Yeah,
But
exactly. Yes.
but yeah, I'm happy to talk a little more about that. So basically, like if you want to scroll down to figure one,
Sure, let's take a look
you
at one, like curve
so
cadence.
so you can see here that figure one shows the long cadence light curve for Papayu, and Papayu, it has actually 17 quarters of long cadence data and 1 quarter of short cadence data.
Okay.
So the reason that like if you think about the data that Papayu has, and just to clarify, long cadence means a 30-minute exposure image is taken versus like short cadence, which is like every minute. So there's a difference between
Yes.
long and short cadence. Long cadence is going to measure more of the longer period oscillations rather than short cadence, which is looking at it like at a higher frequency. So you
Yes.
can see like the minute-long asteroseismic oscillations in the
Yes.
short cadence mode.
Uh-huh.
And it's kind of surprising that it is this benchmark star that we've found, because we only have like 1 quarter, which is like a month of data that is in short cadence
Okay.
for Papayu. So just to sort of recap a little how we found this data.
Okay.
So we had about a sample of like 4,000 or so stars, and then we filtered them with the detection probabilities using like the revised Gaia parallaxes.
Okay.
And we filtered out like um, it had to have a detection probability of greater than 0.9. And when we did that, we had a sample of like 200 or so stars.
Okay.
And then out of that, Papayu was the star which showed the highest signal to noise ratio. So
Cool.
at that time, we didn't really know the age of Papayu, right? Like we would have to do a lot of work to find that age.
Yes.
But we did know that Papayu was one of the highest signal to noise ones out there. And to
Uh-huh.
get
Good.
to get the age of these asteroseismic oscillators, like we need to do like frequency modeling, which is a really intensive process. And so the higher the signal to noise is, the better and the easier it is to do that modeling on it. Um, so figure one was actually just the rotation period.
Mhm.
And yeah, we narrowed down our search to Papayu because of that. Yeah. And so when we think about
Cool.
sort of the different things that we can get from astroseismology, of course, we can get the global parameters because these astroseismic waves, they probe the interior of the star, so you can understand the density, you can understand the mass, but you
Cool.
can also, if you do the frequency modeling, then you can understand, you can know the age, because as people know, like stars would evolve like an onion in layers with different densities, and so you can figure out the age through that.
Cool. Okay,
Yeah,
got it. Cool.
yeah.
Mhm.
And then that figure 1 shows you a rotation period of like 21 plus minus 0.08 days. And so you can see that visually
Yeah,
as well
yeah.
when you look at the crest and the troughs of the figure. And so this makes Papayu a star which has a well measured rotation period, but also is now going to be a star with a well measured age. So now
Okay.
we're going to get into how we measured the age for Papayu. And so we can go now to like the next figure, figure 2. And figure 2 is actually it's just showing you like a astroseismic HR diagram. And so on the x-axis, you can see there's effective temperature.
Mm-hmm.
And on the y-axis, you see there's radius.
Yeah.
And you can see that these these different dots represent different things. The filled circles, the filled and sorry, the filled circles
It's all good.
show
Okay.
show
Take.
rotation periods from McQuillan, and
Yep.
basically they also show the stars that have an astroseismic age already measured. And
Ah,
Papayu, if you notice, is in pink. So that's KIC 1102951
yes.
That's Papayu.
So well.
And so that pink dot is just one out of like 10 astroseismic rotators in this entire sample.
Mm-hmm.
So this sample is like an astroseismic sample. So this is an astroseismic HR diagram. If it's filled, it has a rotation period. If it's not filled, it doesn't have a well measured rotation period.
Okay.
And Papayu is one of the stars. So you can see how small that subset is,
Yeah.
and you can see why it's important to have
Yeah.
a star like Papayu there.
Okay. And what are the gray lines in this figure?
Oh
Curve?
yeah, those gray lines are the missed isochrones. So you can
Isochrones.
generate them yourself
Okay.
using the code developed
Okay.
from MIST. Yeah.
Okay. Isochrones. Very good. Okay, I'm with you. Cool.
Yeah. And then after that, we can actually skip to, I guess we can go to, why don't we go to the extra figure actually?
You want to go to the X figure? Okay.
Yeah.
We're gonna bop out here for 1 second, people. Hi there. I'm bopping
Hello.
around. Hello, everyone. I'm bopping around here. So boom, back there. Let's go back to the share and back in. Here we go. Extra figure. Bonus extra figure.
Yeah, so this is just a figure I'm just roughly showing to show you kind of the process. So if you see like there's a little square plot with pixels,
Mm-hmm.
that's actually how Papayu would look to Kepler. And then there's an aperture through which we are measuring. And to let you know, there was a reprocessing of the Kepler archival data processing, which resulted in like better apertures that were more optimal.
Mm-hmm.
So that's how we actually found it, because in an earlier data release, Papayu was not found with these detection probabilities. And so we were able to find it now. We were able to find these now with a changed aperture. And so you can see that there's a light curve, flux is on the y and time is on the days, time is on the x-axis.
Yes.
And then we do a Fourier transform of that. And so that's actually what you will be seeing in this paper, because I haven't shown the short cadence data, but the light curve in that plot is the short cadence data.
Yes.
And we've normalized that light curve actually with a box filter of like 0.05 days to remove any periodic variations. And we've also removed any instrumental effects and stellar variability. So we have like a normalized light curve, and we take the transform of that. And then also, just to go back to the star quakes that I was referring to, just to give you a visual understanding of what that would look like, you can think of a star as like the surface of a drum, but it's like three-dimensional. So like a radial mode is just like in one direction, like it's either up or down. A dipole mode is like up, down, and the quadrupole I really can't do it with my hands. But yeah, it's like messier. And so I just want to give you that visual understanding, and then also explain like we are not able to really see higher order modes. I mean, there are, of course, a lot of higher order modes.
Sure.
With the sun, we can see those higher order modes because it's closer. But with Papayu, which is further away, we can only make out these first three modes. And
Okay.
for like for most stars, we are able to make these three out. And I mean, if we're lucky, we're able to see these three.
Yes.
Okay, so we can go back now to the paper.
Okay. Hello, everyone. I'm going back. Bang. And back we go. There we go. Okay.
Yeah, so that's a little bit about how we've gotten like how we prepared the data. So that was
Right.
the section about that. But just to like now just to look at the next figure. So
Okay.
I think that is figure 3. So in figure 3, you can
Oh, yeah.
see you can see now that Fourier transform. You can see how that actually looks. And so the astroseismic oscillation, it's actually really difficult to know where that is unless you're using one of these. And so it's kind of right above that pink dotted line,
Yeah.
that pink dotted Gaussian type of shape. It's like
Yes.
right above there.
Yes.
And so that is the data that we're using to actually find Papayu's age. So you can see that there's a lot of variability. There's a lot of noise here. There's a lot of things that need to be removed. And this noise is actually natural to the star, and it's part of like stellar granulation. And so what we've done is we've fitted these models. So the blue dashed constant line, that's the white noise model.
Okay.
The purple dashed curves are Harvey models. And the dashed orange line, that one is like, sorry, that one, let me just look. Yeah, the dotted orange line is the height of the oscillation. So that helps us know where to put the Gaussian.
Okay. Okay.
Yeah. So we've given all these estimates and then we've combined all of it to create this green curve. So the green curve actually is the background that we want to remove. So we want to take this out of this Fourier transformed light curve.
Okay. Cool.
And so we had to measure all these parameters really well. So you can see table 1 shows the parameters for this background fit. And these are all the statistical parameters used for every single one of those curves.
Okay.
They all have different posteriors for the statistical fits. And after fitting them, we have the posteriors in the appendix. And you can take a look at that in the paper if you're interested. It's Appendix A. It shows the posterior distributions.
Yes.
And so once we have this background fit, then we can do the mode identifications and look at the power spectrum.
Yes.
So if we go to the next figure.
Okay. Scaling CD diagrams, and here we go. Oscillation frequencies for Papayu.
Yeah, so these oscillation frequencies are now, just that little bump has now been normalized here. Or not normalized is not really the right word, but it's been background subtracted.
Yes.
And then each of these frequencies has been fit. So so just to let you know, it has about 15 different frequencies we fit, which meant about 45 different parameters.
Yes.
And so these 45 initial guesses had to be provided to the Diamond software. So shout out to like the Diamond software that's helped me do the backgrounds and this is called peak bagging, the peak bagging frequency fits.
Okay.
So each of these observed frequencies from Papayu's light curve have now been fit. And so table 2 shows the best fit values for these frequencies. And for astroseismology, these frequencies are like kind of like gold. Like if you have this, you can like know so much. Yeah, it's like the thing that you need the most. Because once you have these frequency values, you can figure out the age and you can do the modeling to get you there as well.
Yes.
And then you can see like below there is an Eshel diagram as well.
Okay.
So
take a look at an Eshel.
While
okay, there's an Eshel.
That's figure 5. So remember like earlier when I had shown that image about the radial quadrupole and dipole So these are the different frequency modes. So I think of it kind of like, I mean, it is spherical harmonics, but if you want to think about it in a more intuitive way, like sometimes it helps me to think about like the hydrogen atom actually, and to like make that parallel
Yes.
between like
Yes.
hydrogen atom spherical harmonics and like a stellar spherical harmonics, because it's the same physical principle. Um, and so that's the way I think about these. So in the earlier figure, those modes that we identified were not labeled according to the order of the oscillation.
Yes.
However, here they've been labeled, and the reason this plot looks so different is because it's actually stacked. So if you think about like the distance between one radial mode and the next radial mode,
Uh-huh.
that's called delta nu, which is a large frequency separation. And
Uh-huh.
so we stack that power spectrum in chunks of delta nu. And
Got it.
so the
Okay.
width of that x-axis on the shell diagram is actually delta nu. And so it's stacked, and it just makes it easier for us to see all the modes
Perfect.
clearly, and to understand those separations,
Cool.
because we also look at the separations between the quadrupole and radial modes. And these tell us different things, and we can use this to get different parameters.
Very
Yeah, that is one of the uses of the Eshel diagram, and it just makes it all very concise. So that's why it's different shapes for the different modes,
yeah.
to make it easier to see.
And here's our
Um,
mode, and there's our NL values.
yes, yes. Yeah, and so you
Mhm.
could take
Line width.
a
Okay.
greater look at that. Yeah, the line with the amplitude, the
Okay.
frequency, and all the errors.
Cool. Very good. Okay.
Yeah. And so
Wow.
once we found
Really.
these frequencies, then we actually did a preliminary astroseismic age, using an astroseismic HR diagram, and our age estimate was like 3.64 gigayears, plus
Okay.
minus point 0.3.
Okay.
And this is just a preliminary thing we did, just so we can sort of have an idea
Mhm.
going forward. But then
3 gig
to
here.
get a more robust age, we had to use modeling. So we used the MESA stellar evolution code. And so
Okay.
again, shout out to the developers of MESA who have made that possible, for people to model stars in this way.
Okay.
And so we were able to input all these well-derived frequencies from diamonds, and we're able to create a model, and we're able to run it.
Got it.
So all these parameters were provided into MESA. We had multiple runs to obtain the best fit with all these observed frequencies. And finally, we've also used like a cubic surface correction scheme,
Oh,
just to
okay.
adjust for the disparity between the modeled and the observed mode frequencies, because of the inaccuracies in modeling, like near surface stellar layers. And
Yes.
so to adjust for that, we've done that. And then with MESA, I got a result of like 4 plus minus 0.2 gigayears. And we've also actually checked this with multiple co-authors. So multiple co-authors did modeling, which is why they were like, they have also been very essential to this project.
Go ahead.
And they've modeled these observed oscillation frequencies using their own stellar evolution codes and modeling methods.
Okay.
And basically the age uncertainty is like 10%, and the value agrees within 4% to alternative estimates.
Pretty good.
Um, yeah, and so it it gives us what we sort of wanted, which is to
Cool.
make sure that we are on the right track with
Yes.
Papayu's age.
It's about 1.3.
Um,
Okay. Okay.
and, and so you can see that actually in the next figure too, which is figure 7.
57.
So
Diagram. This time all labeled up and
yeah,
marked.
yeah.
Mhm.
So this time I removed the background that shows you the intensity actually,
Mhm.
just to
Yes,
make it
of course.
clearer, because
Rainbow.
here there are a couple different things. So the empty shapes, these empty shapes are showing the MESA frequencies, which were the observed ones. So these are the ones that were in the previous sort of
Yes.
figure. that
Yes.
we saw. But then the dots, the filled circles, these are the figures that we actually care about. These are the points we actually care about matching to the shapes,
Yes.
because these are the points that are surface corrected. And so you can see that the surface correction in astroseismic like stars, it adds a huge difference, because all of the crosses, these are all without the surface correction estimates, and then we corrected it for that,
Got it.
and then we have it in agreement with the observed.
Very cool.
So you can think of the filled circles as the modeled, and the unfilled shapes as the observed frequencies.
Observations. Right. And so this is also.
And then the colors are, yeah, sorry, go ahead.
I was just going to say, it's showing the importance of that surface correction term, right? Because they all
Right.
heavier one and moving back.
Yeah, and also the colors correspond to the different modes,
Radial,
like the different harmonic.
dipole, and quadrupole over here in green. Yep.
Yeah.
Very good. That's a good match.
Yeah.
That's a really good match.
Yeah, and then we also had a age estimate from chromospheric activity. So the calcium H and K lines, and that provided a good estimate to our astroseismic age as well.
Very cool.
So I just want to mention that.
Okay.
So now that we've understood, so far mainly we've just talked about the age and the parameters for Papayu. I really haven't gone into the other parameters. I've just focused on Papayu's age. But now it's time for us to think about, like, what does this really mean? And what it really means is when we tie it into the rotation aspect, right? So if we go to figure 8, we can see how the rotation period scales as a function of stellar age. Okay. So rotation period is on the y-axis, stellar age is on the x-axis. Okay. And these are actually showing for all the astroseismic gyrochronology benchmark stars, the rotation period and the age and how they correspond. So this provides like a comprehensive overview of these astroseismic rotators.
Okay.
And so Papayu is actually like the star-shaped star.
Right here, right next to the sun.
Yeah. And so I just want to point out that these stars are colored by their zero-age main sequence temperatures. And the reason that's done is because the zero-age main sequence temperature is a function of mass and metallicity. And so it selects stars with similar structures and convection zone depths. And these convection zone depths, they are sort of connected to the Rossby number, the convection overturns timescales, and basically stellar activity, which is an important parameter in magnetic braking. And that is the one thing that we are trying to understand, because the magnetic braking of stars and the way it connects to spin down, that is not a completely well understood concept. The physics of convection in stars is still an active area of research. And so understanding those details and making those connections is sort of what this study is partially doing.
Cool.
And so, these so these are showing all the astroseismic rotators, and it also will show you the sun there. So you can see in that plot itself, in terms of the astroseismic rotators with rotational modulation, Papayu is the closest to the sun in terms of rotation and stars.
Yes.
It's actually kind of
a little younger. No.
Yeah, no. I mean, there are certain differences with the sun and Papayu. Like the metallicity is different for Papayu, and that is important. But in terms of the stars that are known astroseismic rotators, it is close enough to the sun that it provides us with some more information for a solar-like star.
And I got one question on this plot. We have some that are like fainter than others. Does that mean anything?
Yeah. So
faded out.
Yeah, so the fainter points, they show the rotation period measurements with the uncertainties that are more than 10%. So you can actually see those error bars on those are much bigger.
I'm good.
Yeah.
Okay.
There's a lot of them, so I made them fainter so you can see the
Got it.
smaller errors. Yeah.
Okay. Thank you.
Yeah. And so then we can actually move on to figure 9. So figure 9 is actually just the subset of this figure, and it is just the closest sort of rotators to Papayu.
Got it.
So this is, again, Papayu is the star shape. But the things I want to point out about this figure,
Yes.
we need to ascertain whether Papayu experiences weakened magnetic braking or if it undergoes a standard spin down. And so to do that, we need to plot these tracks, and these tracks shout out to Keohoku and Slater et al., like all those papers that make the software available to us. But these spin down tracks were calculated using Keohoku and the spin down models. And so basically what this shows is that Papayu sits at the transition of two different spin down models.
Well, that's great.
Yeah. And so
Like that.
the stall spin down model, which is the one in dark gray, that is the model that we are sort of like the community is slowly developing more and more research that is showing that that might be what stars are experiencing as they age, because the standard spin-down models are also based on like stars in open clusters and younger stars. So
Sure. Crap break and all.
I
Yes.
mean, at this point, the stall spin down model provides like a better match to this sample. And so it kind of confirms the preference of like a weakened magnetic braking law. And so that's kind of what we're hoping to understand, because actually, if you think about, if you just think visually on this plot, if you wanted to find, like if you looked at the rotation period of like, let's say 30 days, or actually let's say like 25 days.
Okay.
And if you look at that rotation period, you can see like the age, depending on the spin down model you choose, would change by a couple gigayears. And so knowing which model these stars are following is really important. And Papayu sits at the transition of both the models, with a preference towards the weakened magnetic braking or the stall spin down model.
Okay.
Yeah, and so that is sort of one of the conclusions, but I'll go into the other conclusions as well. So just to recap a few parameters. So Papayu's metallicity is 0.3 dex, and its temperature is 5,888 Kelvin. And then we get its mass is like 1.3 solar 1.2 solar masses and radius of 1.3 solar radii. And we also are able to get its asteroseismic age of like 4 gigayears. So in terms of the Kepler stars, which are asteroseismic rotators, Papayu is one of the most similar ones to the sun in terms of its asteroseismic age and its rotation period, which was 21 days.
Cool.
And so it is also anchoring the onset of weakened magnetic braking, because it's at the transition where both the spin-down models diverge.
Come back to that.
And so in the future, like a comparison with stars of similar ZAMS temperatures will help us see that we can spin down models are preferred. And Papayu helps us anchor that. And it'll also allow us to test the composition dependence of like these spin down laws, because it has a higher than average metallicity. Yeah, so that's sort of where I end this paper, but I also want to say we do have a lack of calibrators in this regime. And so understanding where this anchoring is happening, understanding where weakened magnetic braking starts itself, that is sort of the purpose Papayu is serving here. And so knowing that helps us refine our laws and refine our studies further in that regime. So I just like to thank everyone involved in this project, all the grant funding we have received, as well as all the people I have worked with, including all the different students and all the different peers that I showed all these plots to. So thank you everyone for your feedback. And special thanks to my family and the people of Hawaii for letting us use the Keck telescope, the indigenous Hawaiian community, and everything that made this discovery possible. So thank you to everyone and everything that made this happen. So I'm happy to talk about any future steps if you'd like. Or
Yeah, and
anything.
I want to congratulate you here on your first author paper. Very good. Congratulations.
Thank you. Thank you so much.
Everyone remembers their first one. Very good. Vanshree, I want to thank you so much for walking us through your very awesome article here. And yeah, you did kind of touch on it there a little bit toward the end, so I'm gonna push on it a little bit. Of course, it's really exciting to have one that's right at the transition point, and so you know, we're not going to be waiting around another couple billion years to see which track it follows. So you know, are there other candidates? Maybe not. Maybe that doesn't have the same signal to noise. Maybe it's a little worse. But are there other candidates around there so you can kind of distinguish maybe which track? Magnetic braking track the stars are taking. Are there possibilities of using other wavelengths? How about future astroseismology missions like Plato, let's say, or something along those lines? And just sort of next steps. So where do we go to figure out this? How are we going to figure out this magnetic braking law? Observation.
I mean, I think the more stars we have, the better. The more observations we can make, the more stars we can find through those archival data sets, the better it is. And what actually PapaYu shows is the power of this archival data set. It shows that there's like a treasure trove waiting in these archival data sets to be discovered. So that's like an open challenge to anyone out there who wants to find.
Certainly was.
Who wants to find another astroseismic benchmark star, you can do it. You can look in the data sets and you can do it camera zoom. You can definitely find it. So I think looking at the archival data sets is a start into figuring out all these benchmark stars. And also I know that there's other studies that are being done in parallel that are also that support the weakened magnetic braking law. So I think looking at other authors and looking at other papers that are being published in that field will help us sort of consolidate everything that can be seen, and especially for like PapaYu itself, because of its higher metallicity, we can understand more about the composition dependence of these spin down laws. So yeah, there's definitely a lot more astroseismic oscillators there, and future missions will only increase that number and increase those discoveries. So it is an exciting time for this field, and it's a burgeoning field. And so yeah, there's a lot of scope here for more discoveries to be made.
Very cool. Very cool. Well, I really look forward to seeing this field develop over the next couple of years. It'll be exciting to figure out what stars observationally do with their magnetic braking. Very cool. Thank you so much once again for walking us through your very lovely article.
It's my pleasure. And if you'd like to know more about the kind of stuff I do, feel free to follow me on Instagram. It's my first name and last name. So,
and we'll put a link to that in the description below the video so you can check that out. All right.
Yeah, sounds great. Thank you so much. It was an honor to be here. And thanks a lot for your support on my first author paper. That means a lot to me. So thank you.
Awesome. Very good. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.